Welcome back everyone to our continued discussion of cross-validation. Now we're going to move on to discussing the train, validation, test, split strategy. As we just discussed, we saw that just doing a train, test, split method has that disadvantage of not having a portion of the data that can report a performance metric on truly unseen data. Now, I want to make a point very clear. While adjusting hyperparameters on a test dataset is a completely fair technique, and I'm not going to say it's ever referred to as data leakage, there is the potential issue in regards to reporting. So just doing a train test split is a totally valid method, and in fact, we'll use it quite often throughout the course just because it's so simple, especially when we're just focused on learning an algorithm. But there is an improvement we can make on this. If we want a truly fair and final set of performance metrics, that is, we're running our algorithm on real-world data and we expect it to have a real-world application, I really want to know metrics from a final test set that we don't allow ourselves to adjust on. That way I can know what the model's true performance is on data that it was never adjusted to, regardless of whatever happened before on the validation set. So let's quickly review this process in theory and in application. Obviously, we begin with the entire data set. And then after that, we're going to split it now into three parts: training, validation, and test. As far as the percentage split here goes, it really depends on how much data you have. And mainly what you want is enough test data in that final holdout test set to fairly evaluate your model. If you have millions of rows of data, then you can work with just a very small percentage set aside for your final test set. However, if you're dealing with just a few rows of data, you're probably going to have to hold larger and larger percentages as that final holdout to really get a fair evaluation of your model. Again, this depends on how much data you have. For just kind of the typical case, I would say go ahead and keep training sets at 70% or kind of around there, and then your validation and test set combined could be something like 30%, and from there you can adjust. Maybe make them the exact same size, like 15% and 15%, that's also very common, or make the test set a little smaller, maybe do validation of 20% and a test set of 10%. Obviously this depends on how many rows you have. Okay. So what you're going to do is once you've done the train, validation, test split, you set aside the test set, and sometimes it's called a holdout set because it's going to be for final metrics. And then, as we know, we fit the model on the training set, we evaluate model performance on a validation set, get some sort of error metric, and then we can go back and adjust hyperparameters as needed on the model and essentially repeat this process as many times as needed, where we train, validate, and adjust hyperparameters. Once we're satisfied with this, we're going to perform a final evaluation on the test set. And the main thing to know here is that this is the final error report and you are not allowed to adjust the hyperparameter. The only true purpose of this final test set is to get some sort of metric for your model to just kind of take note of. That way you can report that to your boss and say, this is what I expect my model to perform with on truly unseen and unadjusted data. All right. So again, recall the entire reason to not adjust after the final test data set is to get the fairest evaluation of the model. The model was not fitted to the final test data, and the model hyperparameters were not adjusted based off the final test data. This is truly never before seen data. To achieve this in Python, what we're going to do with scikit-learn is just simply perform the train test split function call twice. We call it once to split off that larger training set, so we'll split off 70% and just immediately label training. And then that remaining 30 we're going to call other, and then we're going to perform train test split a second time to split that remaining data into a validation set and a test set. Let's jump to a notebook to see how this is done. All right, here I am at the Jupyter notebook, and we're pretty much going to start the exact same way as we did last time. We're going to have our imports read in the advertising.csv file. Here's the head. We have TV, radio, newspaper spend, and then the sales. And what we're going to do now is set up the train, validation, test split. This is a really common question I get from students of how to actually do this split into three sets of data. It's really simple. We just call train test split twice. So let's go ahead and show you here. I'm going to set up my features and my label just as we did before. And then we'll say from sklearn.model selection, just as before, import train test split. And then as always, we'll say train test split. Go ahead and save yourself a little bit of time. Do Shift Tab to scroll down here and grab this documentation. Just going to copy and paste the whole thing, and let's overwrite what we currently have. There we go. All right, and I'm going to choose test size of 30%, and we'll explain that in a second. And then we'll say random state is 101, just to be consistent. Now, this is going to be my first split. And my very first split will grab 70% of the data to be the training data. But the remaining 30% is technically not my test data. So what I'm going to do is I'm going to just label this as other. So I have x other and then y other. And this will be 30% of my data that I will then split again to create my validation and test set. So what we're going to do for the next step is I will call train test split again, but now what I'm going to do is pass in x other and y other. There we go. And let's go ahead and now think about what test size actually means here. So I'm going to say test size is equal to, and recall, this is now going to be a ratio referring to the remaining 30%. So what does that actually mean? Well, it means if I say test size is equal to 0.5, that's technically 50% of the remaining 30% of the other data. So that eventually the total test size is equal to, in this case, 15% of all the data. Now, is 15% a reasonable number? Totally depends on the context of the situation. As I mentioned, if you have millions of rows, what you're going to do is probably give the final holdout test set to be kind of a smaller number. However, it's not uncommon to just have the validation and test be the exact same size. So what we're going to do here then is we're going to say that x eval, comma, x test, comma, y eval, and then y test is equal to train test split x other, y other, and then I'm going to say test size is 0.5, splitting this up into a validation set of 15% of the total and a test set of 15% of the total. All you have to be careful of when you're running this is to make sure that the validation sets, or eval sets here, are marking up and lining up as you expect. So recall, the order does matter here of what's going to be validation versus what's going to be test. So always keep that in mind, because it can start to get a little confusing since you're using the parameter test size twice. So things to keep in mind, always kind of carefully think about that. And if you want this to be consistent, we'll go ahead and say random state is equal to 101. All right, there we go. Looks like we're good to go. And just to confirm, you could also check the length of things. So if we check the length of the original data frame, it's 200 rows, which means the length of xtrain should be 140. And then I can check the length of xeval, which should be 30. And then the length of xtest should also be 30. Okay, so 140 plus 30 plus 30, that's 200 rows total. Perfect. So now that we have our three sets, we're pretty much ready to go. Next step is to quickly scale everything. This is all going to look now very similar to what we just did in the previous process. So say scikit-learn preprocessing, import standard scalar, run that, create an instance of the scalar, and then we're only going to fit the scalar again to the training data, just as before. I don't want any leakage coming in from the validation set or the test set. And then what we're going to do is we're going to basically have to scale everything, including xtest. The reason for that is because the model will be trained on scaled data, so it can only validate its performance on scaled data. So we're going to both scale validation and test. So we'll just simply say xtrain is equal to scalar dot transform xtrain, xtest is equal to scalar dot transform xtest, and also xeval is equal to scalar dot transform xeval. And technically it doesn't really matter what order you do this in. Okay, so now we have our three sets, xtrain, xtest, and xeval. Now the next thing is to create a model, and we're pretty much on track just as we did before. So I'm going to quickly create a linear model. We'll go ahead and have it be ridge again. Whoops, from scikit-learn import ridge. There we go. And let's again choose kind of a poor choice. So say model 1 is equal to ridge, say alpha is equal to 100. So then we're going to say model 1, fit it to xtrain, ytrain. So now we have the fitted model. Next one I'm going to say 𝑦_eval predictions is equal to model.predict off x evaluation or validation. Run that, and now let's actually check the metrics. We say from scikit-learn metrics, just as we did before, we'll go ahead and say mean squared error. Run that, and then should get the mean squared error that we did last time. So we'll say 𝑦_eval. So those are the true validation sets. And then we'll say 𝑦_eval prediction. So this should be pretty much almost the exact same thing we got before, because I'm using the same random state as before, and X training right now is the same 70% of data. So why is it not exactly the same as before? Well, for one thing, is that recall, this 𝑦_eval or validation set is essentially half of the data points I had in my previous test set. And the reason I know it's exactly half of those same data points is because I used the exact same random state. So recall, x other and y other, that would be equal to my original just test data if I only did a train test split, which means I know that kind of remaining 30% happens to be either an eval or in test. So you should be getting really similar results to what we got before, around 7.32. Obviously, this was not a good version of alpha, so we create another one, as goes the process, and this is what you would repeat over and over again until you got an alpha you were satisfied with on the eval or validation set. So say alpha is equal to 1, say again model 2, and then we're going to fit it to x train, y train. And now we're going to say kind of new predictions, or whatever you want to call this. We can say new predictions eval or validation set. We'll say model 2 dot predict on x eval. There we go. And now let's go ahead and say the same as before. We're going to say mean squared error. I'm just going to copy and paste this line here, except we'll call this new pred eval so we don't get it confused with the original. Run that, and now you notice we're performing a lot better. All right, so now the question is this value here a fair performance metric? And the answer is yes and no. It's fair in the sense that your model was never actually fit to this validation set. However, your model's actual hyperparameters, alpha is equal to 1, was specifically chosen because of previous performance on this validation set. So are we completely blind in a vacuum to the validation set? Absolutely not. You as the machine learning practitioner are well aware of it in choosing the hyperparameters. So what is the most fair possible performance metric? That's where that final test set comes in. This is going to be the final evaluation that, let's say we are fully satisfied with this performance here, and now I just want something to go report to my boss as far as model performance. That's where the test set comes into play. So for the final performance, what we do is we'll go ahead and keep this model. So we say, okay, I am satisfied with model 2. So we'll say then model 2, and I'm going to predict now off my final test set. And recall, after this, there's no going back and adjusting hyperparameters. So then we're going to say y final test predictions, and then I say mean squared error, pass in the y test that we already know, and y final test predictions, and I get back 2.254, which is actually a little better than what we have up here. And this is a very fair comparison because I know my test set is the exact same size as my validation set. These are both essentially the same number of rows, 30 rows. So what I do is I go report to my boss. I would expect this final model in the real world to perform at a mean squared error of 2.25. However, what we're actually going to deploy to the real world is going to be a model that is fit and trained to the entire data set, just the X and Y. But recall, if you're going to train to everything, you wouldn't be able to then fairly evaluate the model on any subset of that same data it was trained on, which is why you now have this final test metric to report right before you go retrain everything. Okay, thanks, and I'll see you at the next lecture where we continue to expand on this with cross-validation.